Okay, so we're going to do an introduction to the implicit differentiation notes. This set of notes, I'm going to do it, I think, in 3 parts. We're going to introduce implicit, then we're going to do some examples where we are using the implicit differentiation, a couple of nuances to how it works, and then we will do some applications of it in the 3rd video. All right, so the first thing we're going to do, implicit, is really just this idea that we may be interested in finding the derivative of an equation that is not solved for y. And sometimes we can't solve something for y. So those items are times where instead of taking the derivative the same way we've been taking the derivative, we're going to need a new method or technique. And this implicit differentiation is actually an application of chain rule. And you just have to remember that when you are taking the derivative involving chain rule, that when you have the derivative of a function, so if you have f of a function g and you want to take the derivative, say with respect to x, that you first have to take the derivative of g with respect to the x and then times that times the derivative of f with the g in it. So it's this idea that we are going to employ the use of chain rule into doing derivatives whenever we have functions that we are taking the derivative of. Now, where this comes into play is, if you recall from, we've already talked about this as kind of old hat, that we said the derivative of y with respect to x is dy dx. Here, the verb, what I'm taking the derivative of, this is my noun, dy dx, the derivative. And then you might have been wondering, well, why don't I, when I take the derivative of x, do the same thing? Why do I do something different for x than what I do for y? And the answer is, I actually do exactly the same thing, I just didn't write it down. I took the derivative of x with respect to x, became dx over dx, which was actually equal to 1. And so it kind of works out that way. Another way to look at this is to think of this as a function, that what you're really doing is taking the derivative with respect to x of a function f of x. And that to take that derivative, you take the derivative of the inside function, which is going to be basically 1, because it's derivative of x, times the derivative of the outside function, sorry, that's an equals, times the derivative of the outside function, which is f prime of x, which we had said is another name for dy dx. So it should all flow together. What you are going to remember when you are doing implicit differentiation is that this y, whenever you see, sorry, I have the hiccups a little bit. Whenever you see y is a function. So that function is always going to require chain rule. It looks super easy when I'm only taking the derivative of y. Now, what I want you to do is contrast that when you are saying something like, for example, what if I wanted to take the derivative with respect to x of y squared? What you have to recognize is that this y squared is a chain rule problem because I have stuff squared, because y is not the variable that I have down here in the denominator. That's not what I'm taking the derivative with respect to. So when I go to take the derivative of y squared, I take the derivative of the inside, dy dx, times the derivative of the outside, 2y. And that's what we're looking at. Now, technically, we've always been doing chain rule and just not writing it. Even when I do the derivative of x squared, I take the derivative of the inside with respect to x times the derivative of the outside, but dx over dx was always equal to 1. So we kind of waved our hands, and I never mentioned it because there was no point to make it confusing. So technically, you've been doing chain rule all along, you just didn't do it whenever there was an x. If the variable that is here matches the variable that's there, then when you do the derivative of the inside, it always ends up being equal to 1. But if the variable that's inside is not the same as the variable you're taking the derivative with respect to, then you always have the derivative of the inside function that you have to start with. And so that's the main idea that is going to be driving implicit differentiation. Now, with implicit differentiation, we're going to do an example where I'm going to do the exact same derivative. I'm just going to find it two different ways. So technique number one, I have this explicit form, which basically just means that I am solved for y. And if it's solved for y, we would do the derivative the same way that we would always do. We would come along, we're going to do that in example 1, and take its derivative. And so we have our take the derivative of y with respect to x, and we're going to take the derivative with respect to x of 2 over x. Now, when you have a derivative in its explicit form, we treat this like a transitive problem. We just keep going because what I have on the left side, taking the derivative, is going to be equal to what I get after I simplify it. So I treat it in this nice transitive format. I might want to rewrite this. I don't want to use quotient rule. It says 2x to the negative 1. So my derivative would be negative 2x to the negative 2, which I'm just going to simplify as negative 2 over x squared. All right? So I will say, back here in the beginning, kind of leading up to what we're going to talk about with the implicit, is that I technically, this step right here, I took the derivative of both sides. But because I had it explicitly solved for y up here, then this derivative, when I took the derivative of both sides of the equation, what I ended up with is a formula for the derivative with respect to x that was a function of x. So the derivative was a function of x. The derivative is only on this side, and it has only x's over here on this side. Because an explicit form of an equation will give you an explicit form of your derivative. And that's what you're used to seeing because that's what we've only been doing so far. Now notice that y equals 2 over x is exactly the same thing as x times y equals 2. The only difference is this is in its implicit form because we have not solved it for y. And that's really all implicit means, not solved for y. So we're going to now take the derivative using the implicit method just to show you what it is, and we will verify after we take the derivative that they are the same as what I got up here in the first way that we did it. All right, so now the key with your implicit differentiation is I'm going to do the same thing I did in the first one, is I'm going to take the derivative of both sides of the equation. So it starts out, and we write or the derivative with respect to x of xy equals the derivative with respect to x of 2. And so this first thing that I have is exactly the same technique that I did above. Now, my problem is that because it's in implicit form, I'm not going to be able to treat this as a transitive and continue my equals going this way because I have things mixed in over here. Right? So I'm going to take the derivative. Now I'm going to go down. And I'm going to go down because I'm going to treat the left side and the right side as two separate things that I'm simplifying. And we're just going to continue putting equivalent equations one below each other. So step 1 in differentiation, show that you're taking the derivative implicitly by showing you're taking the derivative of both sides of your equation. Step 2 is now perform the derivatives. And what you'll recognize, like here on this side, I have a product. So I'm going to need to use product rule where I have my first and my second function. So we go to take the derivative, which would be the derivative of the first, the derivative of x is 1, times the second, y, plus the first, x, times the derivative of the second, and the derivative of y is dy dx equals, okay, so that was my left-hand side of my equation. Now I'm going to take the derivative of the right-hand side. The derivative of a constant is always 0. So what I have gotten that I have written here in green is I have taken the derivative. I signaled that I was going to take the derivative up here, and it's implicit. I took the derivative. This is an implicit form of dy dx. It is not solved for dy dx. And so in some cases we may leave our derivative as that and not actually solve it for dy dx. But typically what some skills that you're going to have after you get this is sometimes we want it to be solved for dy dx. So the follow-up to I have taken the derivative implicitly. I'm done with that part. The follow-up, I'm going to draw a little line here, is after I have done this, taken the derivative implicitly, then they may ask me to solve for dy dx. That's number one, what they could do, which is fairly straightforward in this. If I just take my equation and I'm isolating dy dx, dy dx is right here. I only have one of them. That's kind of nice. So I'm going to subtract y. So x dy dx equals negative y, and then dy dx equals negative y over x. Alright, so now I have this as an explicit formula, explicit form of dy dx, but this is still not quite the same as what I had up here, because notice that this explicit form is your derivative as a function of both x and y. And so this doesn't quite match what we had up there yet. And so step one, they may just ask you to solve for dy dx, and they may be perfectly happy that this has y and x on it. It is still a derivative. I could find a slope, but the only problem is to find the slope, I would have to plug in a y and an x. Now, step two might be, instead of leaving it like that, sometimes they'll come in and they'll say, step two, find dy dx as a function of x. And if they add that in, okay, then what we need to do is we need to go one more step, which is I need to take this dy dx, which is equal to negative y over x, and I'm going to substitute in y equals something in order to get rid of that. Okay? Now in this problem you would have to go back to, if xy equals 2 from over here, then y equals 2 over x. So we would put 2 over x. So my dy dx is equal to negative 2 over x, which simplifies to negative 2 over x squared. Now, you may wonder, why would we do this? I mean, because obviously, if I am talking about, strategy-wise, if I look at this, and I look at these two examples that we have here, clearly it was way shorter to do the derivative in its explicit form than it was to do this derivative in its implicit form. And that answer is, it's exactly true. In this example, I would have done this every day, all day, by doing it the old way, as example 1. Okay? However, there will be times where you have no option but to use the implicit method. Let me just recap the implicit method. We take the derivative of both sides. We indicate we took the derivative of both sides. We use chain rule every time that there's a y. If there is a y in the problem, like there is here, Here's a y. Every time I go to take the derivative of that y, I have to use chain rule, which is the dy dx. Technically, the derivative of y is the derivative of the inside, dy dx, times 1, which is the derivative of the outside. Then that may be the only thing you have to do. You have taken the derivative in this line. But sometimes they ask you to solve for dy dx, so you may have to do the follow-up. Sometimes they ask you to find dy dx as a function of x, so then you have the next step that's there. All right, let's take a look at the next example. All right, when do I have to? I mean, if I don't have to, I'm not going to do implicit differentiation. However, if I have to, I need to know how to do it. When am I going to have to? If I am looking at curves that are not functions of a single variable, that means I cannot solve them for y. Okay? If the powers of y are greater than 1, that makes it very difficult or impossible to solve for y. So I can't get it into the explicit form that I prefer to take the derivative on. So if I can't solve it for y, then I'm going to use implicit differentiation. All right, now, important note number 1. Just because it's not explicitly solved for y does not mean that it can't be. So just like we saw in example 1 and example 2, I much prefer example 1. So if I can solve it quickly, I'm going to do it. So I would never do x, y equal to 2 implicitly unless they tell me to do it. I would immediately go y equals 2 over x. The second thing is kind of a follow-up to this. If you are taking the derivative implicitly, you have to show it by showing that I'm taking the derivative of both sides. And then you will not use transitive format. You will do your work going down the paper instead of going to the side. All right, important note number 2. It does not matter, those of you who have been arguing with me over this, if you use dy dx or y prime. But my preference is dy dx because that y prime gets mistaken for y to the first. I also don't know what you took the derivative with respect to when you put y prime down there, so I prefer dy dx. All right, so let's look at example 3, just as one more example in this video of how we take the derivative implicitly, and then we'll do the next 2 videos for kind of using the derivatives. So it says, for the equation y equals x plus secant of y, find dy dx. And so on this is kind of understood that they're going to want you to solve for dy dx because you have to find dy dx. So I'm going to take the derivative implicitly, and then I'm going to do the first step, which is solve for dy dx. So I indicate that I am taking the derivative implicitly. Oh, and how do I know that I'm supposed to be taking the derivative implicitly? I know because there's x's and y's messed up in here. There's a y there, there's a y there. They're not all on the same side. It's not solved for y. So I know that in this problem, I'm going to use implicit. I also look at it and I'm like, this is not going to be easy to get y by itself because it's in a trig function, not in a trig function. All right, after I indicate that I'm going to do the derivative implicitly, I pay attention to any places where I'm going to have to use chain rule, which would be here and here. I highlight my y's because those are functions, so you're going to have to do the derivative of the inside. The derivative of y is going to be dy dx equals, the derivative of x is going to be 1 plus, now I have to do the derivative of the secant, but it's got a y in it, so I go chain rule, derivative of the inside is dy dx times the derivative of secant, which is secant y tangent y. So at that point, that is the method of taking the derivative implicitly. But because they said up here, find dy dx, that is telling me that I am going to have to take this now, and I am going to have to solve for dy dx. Now this one is a little bit harder than the one that we just came out of because I have a dy dx here and I have a dy dx over there. So you need to get the dy dx's together before you can solve. Don't just say, oh, I'm already solved for dy dx. No, you're not, because there's one here and there's one there. So the first thing I'm going to do is I'm going to subtract this term over to this side. So dy dx minus dy dx secant y tangent y is equal to 1. Now when I get them over to this side, again emphasizing, now I can factor it out. So the point is, collect all your dy dx's to one side, and I'm only going to go this way simply because I ran out of room. I'm going to factor out my dy dx, which is going to give me 1 minus secant y tangent y is equal to 1. And now I'm trying to get this by itself, so this part I'm just going to divide to the other side. So dy dx is equal to 1 over 1 minus secant y tangent y. And so at that point, notice that I have my dy dx over here. This is my final answer, and it is a function of y. I don't have to worry about substituting the y in on this case because they did not tell me that they wanted dy dx as a function of x. All right. Now, before I go to example 4, I'm going to stop this video here and give you a second to go back and reread over that. This next video will give you some things where you're actually using it. So notice I'm going to start asking you for the slope of the curve.